Okay, so today our warm-up question says Q1 has 4 times the charge of Q2. Which free body diagram matches this? Which of these diagrams shows the interaction between Q1 and Q2? Okay, so first of all, let's start with, are these two charges attracting or repelling? We've seen this diagram before, this field diagram. Okay, do these two attract or repel? Let's start there. Attract, yeah. So we're looking for a free body diagram that shows attraction, which means our choices are automatically narrowed down to A or C. Okay, because B and D both show repulsion. So we want to pick A or C. So the question is, since Q1 has 4 times the charge, does it also have 4 times the force? How do the forces compare? I know it's Monday morning, you guys are very quiet. Yeah, they're still equal. Okay, it's still a force pair. Q1 pulls on Q2 and Q2 pulls on Q1, and that is your force pair. They're equal and opposite. Your free body diagram should be answer choice A. Okay, it doesn't matter which one has more charge. It doesn't matter which one has more mass. None of those things matter. When we're looking at those forces, we are dealing with a force pair, and it's an interaction between the two, and they're going to be equal and opposite. So please make sure that you select answer choice A for today's warm-up. Okay, so for today's notes, we're going to be talking about Coulomb's law, which is the last bit of notes for this unit on electrostatics, and it is where we're going to talk about the one new equation. That's it, just one. Okay, new equation, and if you were working on the assignment last week, 1002.3, you weren't, well, unless you looked it up, you weren't able to complete the first half of it, basically, because it was a bunch of calculations using this formula that we had not yet gone over. So after today's notes, you're going to be finishing up the assignment from last week. If you don't finish it in class, it will be homework. So hopefully we can get through these notes pretty quickly so that you don't end up with any homework tonight. However, you do have a CFU tomorrow. It's going to be a digital quiz like we've done before in My Open Math. Okay, so it's one of the ones that is in My Open Math. All right, let's go ahead and get to the notes. This is really not part of the notes so much as it is an introduction, but we did a lab last week, and in that lab we saw pieces of tape attracted to one another. Sometimes they were repelled, but for example, attracted in some of those instances as pictured here. Okay, if I asked you to draw a free body diagram of each, you would need to include that upward force of, I guess we'll just call it tension in the tape, the downward force of gravity, and of course the electric force. That's where that attraction is coming from between the two. If I drew both of them, they would look like this. Okay, but the point is there is a force between the two causing that attraction, that electric force, and today we're going to talk about how to calculate that force. If I give you some numbers and I give you the equation, we can solve for just how much force there is with just a few other variables. Okay, so that is what Coulomb's law describes. Coulomb's law states that the force of attraction or repulsion acting along a straight line between two electric charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This should sound kind of familiar, and if you can see the equation down there, it's going to be bigger on the next slide. It should look kind of familiar. The equation for Coulomb's law is that the electric force or electrostatic force is equal to a constant K times Q1 times Q2, where those are your charges, divided by the distance between them squared. Does anybody know what this equation kind of looks pretty similar to?
Yeah.
It's like you know it, but you can't remember what it's called.
Yeah.
It looks pretty similar to the universal law of gravitation. Okay, and it's because it is pretty similar whenever you look at it. The universal law of gravitation, we had a constant, G, big G, multiplied by two masses, M1 and M2, and divided by the distance between them squared. This is pretty similar. Okay, except now we're multiplying two charges, time a different constant, and divided by the distance between them squared. Okay, and they're both field forces, and the formula for each of the two is pretty similar. The constant is different, and of course we're multiplying some different numbers. But the way that this is written is going to be pretty similar. So you've done math that looks very similar to this. It's just we're maybe dealing with different numbers and with charges. If you couldn't see the equation before, it's a little bit bigger on this screen. But in this equation, F sub E is your electric force. So that's the force of attraction or repulsion. Okay, that is a difference between this and the universal law of gravitation. Gravity was only ever attractive, but this time we can have repulsion like charges repel. Q1 and Q2 in this equation are your charges. So you'll be given an amount of charge that each of these objects has, and those will be Q1 and Q2. D is the distance between them, and K is your electrical constant, which has a value, and it's always the same value, it's a constant, of 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And again, just like before, if you look at the units for the constant, you can tell what the units should be in your calculation. Of course, you're looking for force, so that's where the newtons comes in, but the distance between the two does need to be in meters. Look at the unit of your constant, meters squared. That's got to be canceled out. The charges are in coulombs. We talked about that unit last week in our notes, and there it is, Coulomb squared. It's going to get canceled out. Okay, you're going to end up with newtons as your remaining unit, which makes sense if you're solving for force. Okay, so again, these are what the different variables stand for, and again, you might want to copy down the value of that constant as well, 8.99 times 10 to the 9th. But yes, the calculation does look pretty similar to Coulomb's law, and to the universal law of gravitation. And just like in that law, and just like we talked about in the warm-up, when we solve this, it's going to be the same force for both of them. So if we do this calculation, it's not just the force on Q1, it's also the force on Q2, because those forces are equal and opposite. They're a force pair. So we'll be solving for the magnitude of the force on Q1 and on Q2 because they're equal to each other. The sign, whenever you multiply these values together, the sign of the charges tells you if they attract or repel. So when you solve for it, you can tell if they attract or repel before you do any math, because the question will say you have two charges. One of them is positive 3 times 10 to the negative 6th, and the other one is negative 4 times 10 to the 8th, whatever. Okay, and so when you look at that before you even do any math, if you have a positive and a negative, you know opposites attract. If you have two positives or two negatives, if the signs are the same, you know they're going to repel. And again, both charges experience equal force, just like we said in the warm-up question. Okay, so let's try a couple of examples. This one says 2 charges exert a force of 4 newtons on each other when separated by a distance of 1 meter. Indicate the magnitude of the force when the separation is doubled. Okay, so we're going to do some of these proportional reasoning questions. You know you're going to see them again. We always do. What's going to happen to your force if you were to double this distance? It's in the denominator. Okay, what happens if I double that?
It's squared to 4 times.
So I'm dividing by 4 times, right? Because it is squared. It's not just half as much, it is 1/4 as much. And this is, again, the exact same relationship we saw with the universal law of gravitation. It is an inverse square relationship. So if you move these things farther apart, the force of attraction or repulsion drops off significantly. You don't notice it as much. Okay, the tape didn't move unless you got them pretty close to each other. Okay, so again, if you were to double the separation, you have 1/4 as much force of attraction or repulsion between your 2 charges. Okay, what if you take one of these charges and you cut it in half? You have half as much charge. What is that going to do to your force? Yeah, half as much. Okay, because charge is in the numerator. If you have half as much, this will be half as much. It is directly proportional. Okay, so half as much, it's a direct relationship. Again, be able to answer questions like this, not just the calculations, but also looking at the relationships that are defined by that equation. Questions about these? Again, none of this is new, so we should hopefully recognize a lot of it. All right, so now let's go ahead and try an actual calculation. This one says a balloon with a charge of positive 4.0 times 10 to the negative 7th coulombs is held a distance of 0.1 meters from a second balloon having the same charge. Is the electric force attractive or repulsive? Okay, Alex, what do you think? Would these attract or repel? If we hold a balloon next to another balloon that has the same charge? They'll repel because they have the same charge. Again, we don't have to do the math to answer that part. There's a positive sign here and it says they have the same charge. Okay, so they will repel. Okay, now this part we do have to do math for. What is the amount of electric force? And now we're going to have to use Coulomb's law, which is up here at the top of my screen. Okay, if we plug in, again, this is the same value every time. This is a constant, 8.99 times 10 to the 9th times 4 times 10 to the negative 7th times 4 times 10 to the negative 7th. They're the same. Divided by the distance between them, which is 0.10 squared. Okay, so when you put this in the calculator, and guys, I would strongly encourage you to practice typing this into the calculator that you plan to use whenever you take your quiz and your test. So if you need to get up and grab one of the Inspires, do that. If you have your own calculator, take it out. But I told y'all this last time when we did the universal law of gravitation to practice typing it in, because I said somebody's going to mess it up. Somebody messed it up. It wasn't just one person either. Okay, please make sure you know how to type it in, because I don't want you missing it because of a calculator issue. If you type this correctly, this is the answer you should get. That might be rounded. I can't remember, but it's 0.14384 newtons. Again, try it on your own. Make sure you get the same number I do. If you're not getting that number, we need to figure out what you're typing incorrectly, because something's wrong. Okay, one other thing I'm going to mention while y'all are typing this in. Sometimes students will get confused about the charge, and they will mess up whether it's positive or negative because of the charge of this exponent. Okay, this is a positively charged particle because it's positive 4 times 10 to the negative 7th. Don't look at this negative 7 and somehow think that that makes it a negatively charged particle. That just means it's a really small amount of charge. Okay, it's 0.000004. So it doesn't mean that it's negative, it's just the amount of charge is really small. So don't get hung up on the exponent, look at the charge in front of the coefficient. Okay, and that's obviously going to be the case for every value that we use in here, but in case anybody was confused about that and looked at this and thought it was a negative charge, no, it is not. Okay, so hopefully everybody got this number, 0.14384 newtons. Does anybody have a question about this calculation? All right. Here's a follow-up question. Okay, so same scenario. Here's our answer from the last question if you need to see it again. Follow-up question says, if the mass of the first balloon is 0.01 kilograms, calculate the magnitude of the acceleration it experiences due to this electric force. So I told you there was only one equation in this unit, and there's only one new equation. But I can totally ask you a question like this. You have a force, you have a mass. You can absolutely find acceleration. This is last semester, an easy equation, but F equals ma. Okay, and so you're going to take that force, 0.14384, you're going to set it equal to the mass, 0.01, and you can solve for the acceleration. Okay, in this case, we're going to end up dividing both sides by 0.01, and that's going to give us an acceleration of 14.384 meters per second squared. So again, there's only one new calculation, but F equals ma is pretty fair game. That's something I could give you on your test or on your CFU tomorrow. It's just one little extra step. Questions about that one? All right, let's try another one. This one says a comb with a charge of positive 7.8 times 10 to the negative 7th coulombs is held a distance of 0.1 meters from Miss Darwin's hair, which has a charge of negative 3.2 times 10 to the negative 6th coulombs. Is the electric force attractive or repulsive? What do you think, Gavin? Are these two going to attract or repel?
Attract.
They're going to attract. Again, we don't have to do the math. Just look. This is positive 7.8. This is negative 3.2. That's a positive and a negative. Opposites attract. Okay, so we've already got the first one, attractive. What is the amount of electric force? Again, now we're going to go back to Coulomb's law, and we're going to plug in those values. Here's my constant, 8.99 times 10 to the 9th. Here is the charge of the comb, 7.8 times 10 to the negative 7th, and my hair, 3.2 times 10 to the negative 6th. You'll notice that I did not type or write the negative sign on the charge down here. I have already determined that they're going to attract. That's all the negative sign is going to tell me. Okay, because remember when we solve for these forces, we're pretty much always going to be solving for the magnitude because one of them is going to be positive and one of them is going to be negative. Okay, so you don't really need to put the negative sign into the calculation because when you're looking at these forces, they're always in opposite directions. So one will have a positive charge, one will have a negative charge. So you just need to find the magnitude. Yes, sir.
So the sign doesn't matter?
The sign only matters when you're trying to determine if they attract or repel. As far as the force goes, like the free body diagrams we used, one of the arrows went to the left, one went to the right. So one of them's always going to have the opposite sign of the other. Okay, so if we put this in and if you type it correctly, you should get this, 2.244 newtons. Again, if you're not getting that value, we need to see how you are or where you are making a mistake. So please make sure that you say something to me or to your neighbor or somebody and say, hey, can you show me what I did wrong before you leave today? Okay, 2.244 newtons would be the amount of electric force, which is still up here on my screen if you need to see it. All right, follow-up question. If the comb has a mass of 6 grams and a strand of hair has a mass of 0.002 grams, which experiences a greater electric force? What do you think, Andrew? Do you think that their masses affect their amount of electric force?
Maybe the same.
Still the same force. Yeah, the mass has no role. It's not even in the equation. Okay, so the mass is not going to affect that at all. Those forces are equal and opposite, and this is what I was just talking about. This is why I didn't put the sign in my equation. One of these forces would be positive 2.244. This one would be negative 2.244. It's always a pair, so you're not going to worry about the sign. You're just solving for the magnitude. All right, guys. For the rest of the class period today, you are working on your assignment 1002.3 electrostatics problem set. It's the one you started last Friday, or hopefully started last Friday. You should just have the first half of it to complete because that's where the math is. Now, if you didn't do it last Friday, then you might have more of it to work on than that. But you have the rest of the class period, and if you don't finish it in here, you can work on it at home. If you do finish it and you're looking for something to do with the rest of the class period, I put a Bill Nye the Science Guy episode on slide 23 over electrostatics. It does have good information. It's also Bill Nye, so he's pretty entertaining. From his old TV show. I don't know if y'all watched that in like elementary school science classes, but it's on slide 23 of the notes. And then as a reminder, you do have a CFU tomorrow and you do have a test on Thursday. We do not have a day in between the two because of SAT testing. Okay, so you're going to have CFU tomorrow in class. You can discuss with each other, ask questions, whatever, but we don't have the class day after that because of SAT. Okay, but you will still have a test on Thursday, so don't forget about it. Even though we don't see each other on Wednesday, you do still have a test. All right, guys, go ahead and get to work. If you have any questions as you are working, please let me know.